ground resistance testing as well. We'll look into the handbook in a while. But let's get started with actually what exactly, what's the need for ground resistance testing, and why do we do grounding in first place, what's a ground fault, and look into all those things, and start with the basics. So NEC, let me use the pointer. So NEC Article 100 defines a ground fault as an unintentional electrically conductive connection between an ungrounded conductor of an electrical circuit and the normally non-carrying conductors or metallic enclosures, metallic raceways, metallic earth, metallic equipment or earth. So, for example, a live wire falling on the ground could be a ground fault, right? So that's what NEC defines a ground fault as. So the next question is, why do we test grounding systems? What's the need for doing that? So the main intention here is, making sure the resistivity of the ground is, low. And with time, corrosive soils and, with high moisture and high salt content, and other effects like temperature, they degrade the ground rods. So once they are degraded, there are issues with the fault. When there is a fault, there are other issues like ground potential rise would be there, and it's not safe for people and for equipment. So ground resistance is basically, is an essential troubleshooting tool to, help maintain uptime and availability and prevent any other electrical problems and safety hazards, to prevent safety hazards. It is recommended that all grounds and ground connections to be checked annually. I mean, that's not done everywhere, but that's the ideal scenario. Check your grounding, annually. And if there is an increase in more than 20%, then a corrective action should be taken, whether it might be installing new ground rods or doing something else. An image showing how ground resistance testing is done. So what's a good number? When we are doing the tests, what resistance value are we looking at? Ideally, the ground should not have any resistance. The whole purpose is that when there is a fault, the fault current should directly dissipate all the fault current into the ground, and the soil should not provide any resistance to it, because that fault current would show up at the surface of the soil, and it would cause damage to the equipment, and is an issue for people as well. So 0 ohm resistance, that's ideal, but the NFPA and the IEEE standard recommends a ground resistance of 5 ohm or less. And I think the NEC 2017 Article 250.53.2 calls out for 25 ohm or less. That's the NEC standard for a single ground rod, pipe, or plate grounding electrode. So this is an indication that 25 ohm is acceptable in some applications as well. In some other, sensitive equipment or areas of, 5 ohm or less is preferable as well. For example, the telecommunication industry often has 5 ohm or less. So the goal in grounding, basically, as I said, is to achieve the lowest grounding resistance possible, keeping in mind the economic side of the things as well, and physically as well, because not everywhere we can, have the desired grounding plan that we want to. So both physical location and capital investments play an important role as well. The electrodes, the ground electrodes, can either be clamped or they can be CAD welded. CAD welding is the process that's most commonly used out there in the industry for exothermically welding your ground rods to the grounding conductor. So basically you use the welding powder and ignite it, and it forms a permanent bond between the grounding conductor and the ground rods.